Hello again, and thank you for joining me for another maths video on Stats and Mechanics for Year 13 Edexcel Pearson A-Level. This time we're looking at Chapter 2, which is Conditional Probability. We're going to look at Venn diagrams first of all, and the chapter in itself is going to heavily focus on Venn diagrams throughout. So we're going to start by recapping the basics of Venn diagrams, regions and Venn notation, but later on we'll also see the joys of tree diagrams and how two-way tables can be used in A-level problems involving conditional probability. But for now, let's just have a chance to have a look and get brushed up on some of those older Venn diagram skills. So there's 4 questions to have a go at. These are all Year 12 content to get you thinking again of Venn diagrams. So try these on your own and press pause now, and then press play on the video when you want to see how you've done, and I'll talk you through them. So assuming that you've paused the video and now playing it to see the solutions, let's have a look together at question 1. So for question 1, on this Venn diagram, we need to shade in B dashed. So what is this B dashed thing? Well, to shade in B would just mean this circle B here. But B dashed means everything apart from B. Whatever comes before the dashed means not that thing. So A dashed be not A. Your dog dashed would mean not your dog, and so on. So B dashed is anything apart from this circle. So we colour in everything apart from this circle B. So we get something that looks a little bit like this. Everything apart from the B circle coloured in. This yellow is therefore B dashed. Question 2, on this Venn diagram, shade A, N, B. It looks like an N, but this is actually a symbol which stands for intersection. So A intersection with B, that means where A and B both overlap, where A and B are happening together at the same time. Over here it's just A, over here it's just B, but in the middle is where A and B are together at the same time. That's A and B together, so therefore we colour in this bit here. So that's A intersected with B. Describe using set notation the shaded area in this Venn diagram below. So here regions A and B are coloured in as well as the intersection. So A and B have been joined together in a way. A, B in the middle bit, this is therefore A joined together, unified, this is the union of B. So this here is A unified with B. Both A and B combined into one region. Lastly, question 4, we've got 2 events A and B. As such, the probability of A is 0.2, the probability of B is 0.7, and the probability of A and B happening together simultaneously is 0.16. First, we need to show that A and B are not independent. This goes back to one of these laws of probability, which you may have forgot, but if 2 events are independent, then this rule will hold. So if 2 events are independent, then we'll always have the probability of A multiplied by the probability of B equals the probability of A and B happening together at the same time. So first of all, let's work out what PA times PB is. So the probability of A multiplied by the probability of B, well, it says in the question, luckily, the probability of being event A is 0.2, and the probability of event B occurring is 0.7. So we do 0.2 multiplied by 0.7. However, the probability of A and B, we're told, is 0.16. So this here is not equal to the probability of A and B, which is 0.16. So this bit is not equal to that bit. So therefore, A and B are not independent, because the probability of one multiplied by the probability of other does not equal the probability of A intersected with B. 0.2 times 0.7 is 0.14, I should have probably put, and that is not the same as probability of A and B occurring together. 0.2 times 0.7, I'll just say that's 0.14, which is not the same as 0.16. So therefore A and B are not independent. Now for part B, it might well help to draw out a Venn diagram. So all we need to do here is to get a rectangle or a square to put the stuff in, and then we've got A and B, so we need two regions. So this can be region A, and over here we can have region B. And we can fill in what we know. So A and B together was 0.16. So if I just fill this in, that means the intersection, the middle bit, is 0.16. Next, we can use the fact that the probability of A was 0.2. So if this bit's 0.16, then this other bit, just being in A, must be the other 0.04, because 0.04 plus 0.16 gives 0.2. In exactly the same way, the probability of B is 0.7. If this is 0.16, then over here must be 0.7 minus 0.16. In other words, this will be the extra 0.54. And it's supposed to be complete in this Venn diagram. We should also include the number on the outside, the chance of it being neither A nor B. So we can do that too. And that'll just be 1 minus all of these probabilities. So we can do 1 minus 0.04 minus 0.16 and then minus 0.54. We get there a result of 0.26. So we've got 0.26 on the outside of the Venn diagram. So because we want to find the probability of A unified with B, then what we're wanting here is essentially all the numbers in the inside of the A and B circles combined. So A unified with B, we're looking at all of the numbers added together in this region here. That region in red is A joined up with B. So we just add these together and that's our solution. So P, A joined up with B, is 0.04 plus 0.16 plus 0.54. In other words, it's everything apart from the 0.26, whichever way you want to think of it. But you should get here an answer of 0.74. And that's the warm-up completed. Let's now have a look at working out some harder regions and some trickier problems involving Venn diagrams. So far we've had two different regions, two circles. What if we had more to contend with? So, moving forward, Venn diagrams again for two events, but let's just start with making them slightly trickier. So for A, we need to shade the following, which is A intersected with B dashed. So let's just think of this step by step. So first of all, the region A is just the whole circle A coloured in like so. So region A is all of this red circle A. Now B dashed means everything outside of this circle B. So if I colour this in with blue lines to represent B dashed, then B dashed is all of this area where I've coloured over in diagonal blue lines. As you can see, I've dotted over where the circle B used to be, so no blue lines can go inside circle B because it's B dashed we're after. So we want the union, we want the intersection, the intersection of the red and the blue. So what we're wanting is to find the area where you can see the red and the blue together. And as you can hopefully see, the only region where this occurs is this bit of that red circle. So not the entire red circle, because this has no blue, it's just this bit of that circle. So what we're going to have here is just that bit coloured in. For part B, we've got A intersected with B in the brackets. So A intersected with B, like we said before, that's just where A and B are together at the same time. It means the overlapping bit where A and B overlap each other. These two circles overlap here, so A intersected with B is this region, like so. But because it's all of this stuff in brackets, it means we want this not. We don't want that. We want everything apart from that bit in red. The dash means everything apart from that, of course. So everything apart from the middle bit is almost all of the diagram filled in apart from that middle section. So you invert the colours essentially. So A intersected with B, all dashed, would look something like this. The whole bit in green without the intersection included. Finally, part C, A dashed means everything apart from circle A, which is this region I've shaded in red. I've made it slightly transparent so you can see the A and the B. And also now, considering region B is just the entirety of circle B. So if we add this in like so, using the diagonal lines again, that's all of region B. Now what we want here is to unify A dashed. We want to join together the red and the blue into one. So essentially the region we're going to colour is where you can see either red or blue or both. So colour everything in apart from what's not been touched at all. So we're going to colour in all of this rectangle apart from this bit of circle A. So you should end up with something looking a little bit like this. Now I've chose these particular colours, a yellow, a green and a blue. That's completely arbitrary, of course. What is important is the regions you've shaded in match the ones I've shaded, and also more importantly that you understand why we shaded these particular bits and not the others. Ask me for help or in the comments if you're still not sure. With example 2, let's now move on to the big stuff, if we've got 3 different regions. So Venn diagrams for 3 events now, A, B and C. So first of all, obviously let's start with A. So for A, we've got 2 things to consider. First thing in red is A joined up with B, A intersected with B. So where do A and B overlap? Hopefully you can see it's this bit here in the middle. So I'm going to highlight that in a red outline. It also mentions region C, so I'm going to go over circle C in a blue outline. Now we want the region in red to be overlapping because this is the intersection with region C. So where can we have the red and the blue together at the same time? Well, hopefully you can see it's actually this bit here. This is where the red and the blue cross over and overlap. So the only thing we need to colour in is this middle little bit, which looks like a tiny triangle. That's all we need to have filled in, that tiny middle part. This one here looks very similar. The only difference here is the symbol's been switched, but it does make a huge difference. So once again, we're talking about A intersection with B. So again, this is that bit in the middle, which I'll put in red once again. And region C, again, I'll go over the circle C. This time, however, we want to unify, in other words, join together the red region with the blue. So we just simply combine the red and the blue into one, glue them together, so it's going to be all of the red and all of the blue bits combined. So what we need to do is colour in all bits, so we get something that looks like this. Part C, I always think of the intersection symbol as an N, as in fish and chips. So this means to me, and hopefully to you, A overlapping with B, overlapping with C, A and B and C together. So it means the intersection of all 3. So where do all 3 of A, B and C overlap? Once again, it's the same as part A. It's here, so we're colouring this one in the same way. The final one, we've got these horrible dashes again. So first of all, A dashed unified with B. Well, A dashed just means everything outside of region A. So A dashed is going to be, give me thing very rough and ready here, A dashed is everything on the outside of A. Like so. And we're going to find where that intersects, where this overlaps with circle B. So if I think of circle B being in a green colour, like so, then the intersection, the overlap, is where you can see the purple and the green together. So hopefully you can see here that the only bit where it's going to be the green and the purple is this region here. just that bit. Over here it's just green, anywhere else it's just purple or nothing at all. So for A dashed intersecting with B, we need to colour in this bit in yellow, but I'll do this in a very bold red colour. So that's what we need to colour in first. And then we're going to unify this with C dashed. Now C dashed means everything apart from circle C. So if diagonal lines, I'm going to shade in blue diagonal lines everything outside of circle C, so we get something that looks like this. Now because I'm unifying both regions, it's where we have either solid red, diagonal blue, or both. So the only thing we don't include is where there's complete white. So because we're including either red or red and blue, we're just excluding this one, and that one, but colouring in everything else on the diagram. So you should have something like this. And like I said, only 1, 2, 3 regions remain completely unshaded. So some worked examples, 2 to be fair. Venn diagrams and probability. So first of all, question 1 is about a deck of playing cards. Now this is going out of fashion as a examinable thing. Fewer and fewer people use playing cards like in the olden days, dare I say. So I'm going to try and make this a bit more illustrative for you. So a card selected at random from a pack of 52 playing cards. Let A be the event that the card is an ace, and D the event that the card is a diamond. If you're totally clueless about cards or how many cards are in a deck, don't worry, I'm going to just explain to you now pictorially. So A, B, C and D, we'll come to that in a moment. So 52 playing cards, what are they? So this is a deck of cards. So there's 4 different suits. So the top suit here are called clubs. Then the second row are the spades, then hearts, at the bottom are diamonds. So there's 4 different flavours, 4 different suits, and 13 cards in each suit, where you start with the ace, then count up 2, 3, 4, all the way up to 10, then jack, then queen, and the highest rank is king, but in some card games, ace is ranked higher than king. So let's just think about how many cards are in the deck, different types of cards. So firstly, it's talking here, this question, about aces and diamonds. So let's get a Venn diagram going, where we can think of aces as region A, diamonds as region D, aces and diamonds together in the middle, and if they're not aces and not diamonds either, they go on the outside. So first of all, ace and diamonds. So how many cards are aces and diamonds at the same time? Well, all the aces are here, and the diamonds is the last row. So essentially, it's where does the ace column intersect with the diamond row? As you can see, there's only one card. There's only one way of getting an ace and a diamond, and that's if you pick this one down here, which is the ace of diamonds. So that's one card out of a total of 52. So we can add in one there, and we'll return and answer that question later. So that's one ace, the ace of diamonds. So how about the other aces? Aces that aren't diamonds. Just aces without being diamonds. Well, there's 3 aces above. We've got the hearts, we've got the clubs, and the spades. So these 3 here are still aces, and then all the aces have been taken out. So there's 3 aces that aren't diamonds. Next, because we're talking about diamonds, how many other cards are diamonds that aren't aces? Well, the other non-ace diamonds are down here. So if we look at these next, which I'm going to colour in blue for this region, there's actually 12 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 diamonds that are not aces. So we can fill in 12 there. So how many cards are neither aces nor diamonds? Well, it's all these here in the top right of this image. So it's all these cards. I'm going to colour in a lovely pink. And if you were to count them up, you'd see that would be 36 cards altogether. So this Venn diagram, I think, will help us to answer this question. And if you're not familiar with cards, I'm hoping this helped in some way to understand what cards are, even if you don't end up playing them ever in your life, of course. So first of all, what's the probability of picking at random an ace and a diamond. The probability of picking the ace of diamonds. There's only one card out of 52 that does that. So this probability is 1 out of 52. For part B, we need to work out the probability of it being an ace unified with a diamond. So this means either an ace or a diamond or both. So the union of A and D is this region here. So A and D unified is all of this here. So how many events are there? Well, there's 3 plus 1 plus 12. There's 16 out of 52. So the total probability of getting either an ace or a diamond is 16 over 52. And if you want to, that can simplify, but it's completely optional with probability. This one here, the probability that it's not an A dashed. So it's everything outside of this A circle. So if I just get rid of what I drew on earlier and delete that. So everything outside of the A circle is everything excluding what's in red. So hopefully you can see quite clearly there's only 4 cards that are aces. The other 12 plus 36, the other 42 out of 80 are not aces. So the probability of not having an ace is these other 48 out of 52 cards that could have been picked. And lastly, part D, probability of A dashed joined up with D. So let's think of this a bit carefully. Again, I'll delete that for part C. So A dashed means everything that is not an A. So what we're going to do here is focus on all the cards that aren't an A. So the A dashes, if you like, are all these cards here. It's all the other 48 cards. But I want to have that intersected with ones which are diamonds as well. So where does the region A dashed, the not A's, and what I'm going to do here, I'm going to draw this out in fact. So the not A's are all of these. So there's 48 of them. And where it's also a diamond, well, the diamond bit is this bit here. All of these are diamonds in this blue region. So where do the blue and the red overlap? Well, you can see here it's this one. All of these down here that I'm putting a cross on is where they're all overlapping. So you can see here I've put 12 very fat blue crosses on out of a total of these 52 cards. So this probability is therefore 12 out of 52. Finally, work example 2. So given that the probability of A is 0.3, the probability of B is 0.4, and the probability of A and B together is 0.25, first of all we need to explain why events A and B are not independent. So what we do here is we work out PA times PB. So probability of A multiplied by the probability of B. Well, luckily we're told what these are. So probability of A is 0.3 and the probability of event B occurring is 0.4. So we just times these two together. So use a calculator if you really want to, that's fine, but 0.3 times 0.4 gives us 0.12. Meanwhile, we're also told the probability of A intersecting with B, of A and B happening together. So probability of A and B is 0.25. So we've got 0.12 for PA times PB, and probability of A intersecting with B is 0.25. So therefore, because PA times PB is not the same as this, the events are not independent. So we just say therefore A and B are not independent. And just explain something along the lines of because PA times PB did not equals with a cross over it, the probability of A and B. So PA times PB is not the same as 0.25. So basically 0.12 equals not 0.25. If it did, that would show they are independent. Because they're not equal, they're therefore not independent. So now for part B, we're also told that probability of C is 0.2. And it mentions about events A and C being mutually exclusive and that events B and C are independent. In fact, what I might do, I might just move this slightly up because it may be getting on in some people's way, this. So if I just slide all this slightly upwards, like so, there we go. So what we can do now is think about how we can maybe draw this out for part B. So first of all, for Venn diagram, just do a fairly nice big square or rectangle. Now, we've got three regions now, A, B and C. So we're told that A and B do intersect because there's intersection 0.25. So I can do circle A and circle B. That's no problem whatsoever. So this is A and circle B. They clearly overlap in some way. Because PA intersection with B is 0.25. So we can fill this in already because we're told that. The trouble here is working out where region C is going to go. Because it says A and C are mutually exclusive. What this means here is circle C does not touch circle A. So circle C doesn't overlap with A at all. So the question now is, well, will it overlap with B? The clue here is it says events B and C are independent. So there's a general little fact which helps here. So because B and C are independent, it might be worth knowing this. This useful fact, if two events are dependent, they are mutually exclusive. The converse is also true. So if two events are independent, in other words, we've got here that B and C are independent, then that's a bit of a wonky line, that will annoy me. There we go. Because they are independent, then they are not mutually exclusive. In other words, they will overlap. So this means here that B and C do overlap, but A and C don't. So I'm going to include circle C, which will just be overlapping with B, but not at all touching A. So that's circle C down there. So now we just need to add in all these probabilities as carefully as we can. So we're told here, probability of A is 0.3. This bit of A is already 0.25. Think about as 30 pence, the total for A. We've got 25p already, so this must be the extra 0.05. Probability of B is 0.4, so we need another 0.15 split in between here and also there. So the key is, how do we split these probabilities correctly? And we're also told here that probability of C is 0.2. But of course, B and C are independent. So we can use a probability law to work out the probability of this region here. Because B and C are independent, probability of B times the probability of C will equal the probability of B and C occurring together. We know that because they are independent events. So this line here implies that. So the probability of B is 0.4. The probability of C, we're told, is 0.2. If I get this in a pink colour here, that's 0.2. That equals 0.08. So probability of D we've used, we knew that was 0.4 from here. So 0.4 times by 0.2 gives us 0.08. So we've basically worked out the region where B overlaps with C must therefore be 0.08. So this bit here has to be our 0.08. It did also say that the probability of C altogether is 0.2, which is 0.20. This bit here is 0.08, so we need the extra 0.12 down here. And now we're not far from actually being done with this example. The probability of B, though, was 0.4. So far in region B, we've got 0.25 and 0.08, which totals together to 0.33. So in this region here, we need the extra 0.07. Typically, students will tend to forget the outside number. You're never done until you've worked out if it is a value on the outside. All probabilities need to add up to 1 for any event set, so we need to see if these add up to 1, and if not, the missing value needs to go here. So let's add these together and see what we get. So what we've got here, we've got 0.05 plus 0.25 there, plus 0.07 for just B, plus 0.08 for this region, then plus a final 0.12. That gives 0.57. So if we do 1 minus that answer, we get 0.43. So this region here has to be the extra 0.3. So now, finally, for part C, we need to work out the probability of this awful looking thing here. So let's just consider this very carefully so we don't make a mistake with our shading or whatever, because that's the common way where you'll go wrong for part C. So first of all, the probability, let's work out this section here in the bracket. So A and B dashed, wrong colour. Let's go for this green. So A intersecting, I mean to say, A intersecting with B dashed. So B dash means everything apart from B. So where would circle A touch anything that's not in B? Well, it's got to be this 0.05. So we're looking here. It's this region, just this bit of A. I'm going to unify that. I'm going to join it together with region C. Now region C is all of this region in the circle C, and obviously that totals 0.2, which the question told us. So if we join together the green and the red, probability of A intersecting with not B joined up with C, well, the green bit is 0.05 unified, so or we can have this 0.2 in total in the red. That gives us 0.25 as a final probability. So the key thing here, when we've got Venn diagrams, draw them out carefully. Some teachers may even suggest tracing paper so you can see the overlaps clearly. So highlighters or tracing paper may well be your friends, but most importantly, taking your time will be your best friend in this, and just practice, practice, practice. On the topic of practice, it's now your turn. I'd like you to turn to your books, page 19, and try exercise 2A. The questions I'm suggesting are all of them from question 4 through to question 12. Check how you're doing regularly, either by checking the answers at the back of a book or by asking someone you sat next to or your teacher if you're still unsure. And of course, if ever you do need any extra help, please do see me or leave me a message. And thank you ever so much for actually watching the video in the first place. So take care of yourselves, and we'll see you soon for the next instalment. Goodbye for now.